Where's that?
Under more, where you are. Yes, that's the one.
Cool. Very good. And then I probably need to move Catherine out. I'll move you out to the side here. All right. Good. So I'm going to say a little bit about noise, and that's something we are all interested in, and that in many ways is not really very well understood, I think. And the marine mammal persons are, of course, the way ahead with all this, whereas noise effects on most terrestrial animals is really not well studied, except humans, where there's quite some data on it.
Hang on just a sec. I think we wait until he.
Oh, sure.
Sorry, because he's recording and setting up the text side of things.
Yeah,
so
yeah, of course.
Just hold on.
Cool. While we're waiting, would you allow me to take a picture of you? It's to send to Magnus and show him that we're actually working. He will think that we're wine tasting in Franschhoek all the time. Thank you.
I photographed you without asking permission.
We won't post it on Facebook or anything, unless you want.
Sure.
Is my computer in the way? Is this in the way? No, it's okay. It's okay. Okay, cool. So, as I said, noise is something where the marine mammal people are way ahead of everywhere else, and have speculated much more about the effects of anthropogenic noise on hearing. And in terrestrial mammals, there's not so much known except in humans. But again, what noise actually is needs to be discussed a little bit before we turn on to look at effects of hearing. Because people think that it's a straightforward thing what noise is. And here are some of the definitions. So one is that noise are the sounds you don't want to hear. And that sounds sort of reasonable, because when we talk about the noise, it's usually an annoying thing. But the problem is, what do you actually want to hear? If you walk in the forest and so on, which sounds do you want to hear? So that's maybe not so good. Then you can use it for any sudden, unexpected sound, intense, non-musical sounds, or you could use it as a mathematical formalism. So when we, in many applications, talk about noise, for example, when we do noise stimulation experiments, it's usually a kind of a mathematically well-defined noise. It's either white noise or pink noise or something like that. But all of them have their shortcomings, as we will return to. Mathematical noise, as I said, is random signals varying in amplitude and phase, which is what we call white noise, that contains all frequencies. And if you talk about Gaussian white noise, it has the additional feature that the amplitudes have a bell-shaped distribution, so they have a Gaussian distribution, meaning that they are distributed around a mean amplitude. Actually, noise is more than either of these four definitions, I think, and that is that I think you should have an operational definition of noise, which is that if you have a given task, there are some stimulations, there are some sounds that make it more difficult to do that task, and in that context, that these kind of sounds are noise. And that means that noise is not a specific signal. If you are trying to work on speech, to hear a conversation, then other speech sounds are more disturbing than anything else. If you are trying to catch an animal based on its rustling sounds, then these kinds of noises would be other extraneous noises would be more damaging and so on. So there's no special characteristics to noise in that respect. And what does this do to animals? Yeah, if we, why did that now happen? So Okay, I just need to get through. Hi Catherine, I just need to get, good to see you, I just need to move you away a little bit. I'll put you up in the corner here. So you're virtually back in South Africa, Catherine. Okay, so if we list them here, it's listed in terms of severity, as you can see. So the least severe is that any noise, any sounds that the animal can hear that sort of interfere with its task might make behavioral changes. And the simplest behavioral changes you could say was that if you have a frog, for example, we just studied fire-building frogs in Romania and tried to expose them to noise. If you have the frog that calls in a certain rate, it will change its rate of calling. Right? It will typically slow down, and if the noise is periodic, it will place its call outside the noise bursts. Right? And that in itself is, of course, it makes its calling rate a little bit lower, and therefore, of course, it affects its chances of attracting female frogs. Right? But other behavioral changes could be that the animal simply moves away, that it avoids the noise sources, which also can be important enough. So that you could say was the milder effects, but still effects that are deleterial to the animal's fitness, maybe. And the severity will be, it depends on how rare and how endangered this animal is. Right? If there are only 5 or 50 left, then you also need to worry about these things, right? Because you cannot afford to lose a few of them. The next one is masking. I'll get back to what we've already discussed that, but I'll show a little bit more about masking. Then you get into the more the darker areas here, and the first one that you would see is what is called the temporary threshold shift, or the fatigue, auditory fatigue, which means that the thresholds will be raised for some time and then they will revert to normal. We still think that this reflects some a threshold for physiological effects of the sound, but they will eventually be repaired. I should say though that in the mammal world there's debate on how repaired they are, because it's thought that even if you revert to the normal audiogram, you might still have lost some of your sensory neurons, and there's a literature on that. But anyway, in the bottom end we have the physiological damage, and of course that could be damage to the auditory system itself. In mammals that would most likely be damage to the auditory, to the outer hair cells. I thought I have a picture of that somewhere. Or you could have, if it's really severe, you would have burst your eardrum or so, or have damages to. But that is on the level of cannon firing or so on. so that's rarely happening. And then, of course, and that's often underestimated. Can be a systemic response to sound too. For example, in humans, it is known that people that are exposed over a certain level will have an increased risk of heart attacks simply because their sleep pattern can be disturbed when they sleep near roads. That is difficult to see, right? But it has nevertheless been shown that there is a stress response to intense sound stimulation. So, that just froze. Okay. Sorry about that. Okay, I don't know what that was. So if we look at some few examples, And if you're interested in this stuff, there's a book in the Springer Handbook of Auditory Physiology series. 16 is wrong, it should be 18. 2018, edited by Slabekorn, where I stole some of these pictures from actually. So if we look at behavioral responses, it could be change of activity pattern during the day, it could be changes in call rate. All these responses are also responses to natural sound sources. I mean, if you are a frog calling in a pond where there are many different species, you'll see that they space their calls nicely so they don't overlap. And of course, one of the worst maskers of a frog will be frog of the same species, other male frogs of the same species. And this is going on all the time, also in the absence of anthropogenic noise. And in a way, it doesn't make sense to distinguish between anthropogenic noise and natural noise. They work the same way, of course. Ole has also already mentioned the Lombard effect, which is that you increase your call amplitude in the presence of noise. And then there's the avoidance. Animal will generally avoid places where there are intense sounds if they're not interested in the sounds. We see that, for example, also, my best example is, I think, is actually from marine mammals in Denmark. We see that harbor porpoises, for example, avoid very noisy areas, and then, for example, during a construction, and then come back again. And again, it's not a problem if the animals are not endangered or critical, but it can be a problem if you're dealing with rare animals, of course. This is an experiment with a marmoset, and I don't know if you can see it here, but they are exposed to noise in the noise bands, bursts of noise, and you will see that they nicely place their calls between these noise bursts. But again, frogs will do the same natural response to other mates of the same species. So this is a little bit about masking, and what does masking actually do? It masks by interfering with your signal detection or discrimination. So this is an example. If you try to detect a signal, which could be a tone, to detect whether a tone is on or not. The thing that you do is to create an auditory filter, which is based on the filtering response of your inner ear. Basically, in us, that would be the cochlea. So that creates a filtering around that tone you detect. You try to detect, and if you have noise at the same time, it affects the detection of that tone by putting some energy within that filter. And the more energy you have in that filter that is not the tone you try to detect, the more difficult it will be. And this leads to that you can define that filter in psychophysical measurements, and that's very important for what the animal does, how vulnerable the animal is with the noise. If you mask the audiogram, it looks like I should have had a picture of all equal loudness contours. What you see is generally that the thresholds are shifted upwards and the audiogram becomes flatter if you have a wideband masker. And if you mask the threshold, then at the threshold you will have as much energy of the masker as of the signal you detect in the filter. And if you can control the band of noise here, you will see that if it's outside the filter, all this noise energy doesn't contribute to the masking. But as you reduce the band, you will see that at a certain band you start to have less and less and less energy of noise in the filter. And there the masking efficiency will go down, so the thresholds will go down, right? It will be more easy to detect the signal that is here. So all this energy masking, you can explain from the filtering that the inner ear, the cochlea, is doing, and from the traveling wave and the amplification of the traveling wave. And actually, from such simple masking experiments that you do, where you all the time ask a person whether you can hear the tone or not, you can actually construct the filters that corresponds to the vibration of the basilar membrane in the cochlea. So that's one of the glories of behavioral psychophysics. So, but how does this actually work if you look at it from the neural level? And it works like this. Imagine that you are looking at a lot of nerve signals, and you have to decide whether there is a signal, whether there is a predator out there or not. And you should do that just by looking at neural activity like this. If you have masker on, then you increase the neural activity, right? And then having an additional signal on becomes much more difficult to detect because of that. So you're simply making the job more difficult to detect the sound. So this is masking. And what is the effect of masking? Well, the prime effect is decreased audibility. So you have a harder time hearing that there's something going on. That can of course be very serious. That can lead to increased vulnerability to predation. You have more difficult time hearing that a predator is coming. You have a more difficult time hearing that where your mate is, and you will have decreased communication ranges. And this is a model or a review from Bob Dooling from the same Slapcorn book, where he has looked at, there's a masking level here, and he has like these four curves. They have four different behaviors of the bird. So the yellow one is the ability to detect the signal. And the black one is where you can communicate comfortably, and I can't remember what the blue and the red is. The blue one is discrimination, and the red one is recognition. Sorry. So you can see that the distance where you just can detect that there's something is always the longest one, but the distance where you can reliably communicate is a short one. And if you have a masker on, if you have a masking noise like traffic noise, then it will reduce the level where you can communicate reliably, but even also the levels where you can detect the sound. Yes.
So with a filter, is that something that I'm just going to think of and think, okay, I'm listening out for a high-pitched sound amongst this traffic noise. Okay, now the filter's on. Or where does that filter come from, in the brain or in the ear?
the prime place of the filter is your cochlea. I mean, because you can, from these filtering functions that you measure psychophysically, you can calculate back to excitation patterns of the cochlea.
Okay, so the animal thinks, or doesn't even think.
The animal doesn't think. The animal tries to hear the tone, right? It tries all the time to hear the tone or what it needs to do. But if you have a trained animal, it would try to hear the 6 kilohertz or whatever it is, right?
So a baby lion isn't going to be able to have a filter.
Oh, they will all have a filter. I mean, they all have a filter. They all have a working cochlea.
Oh, yeah. But to look for the mother's call amongst the storming winds or whatever, it'll struggle more than an adult lion. So it's like a learned experience.
I mean, it has to learn what the call is like, unless it could be innate, I guess, if it's the mother's call. But it will improve as it's probably as its cochlea grows. But it would still be able to perform it in the same way. And the filters are there no matter what. And if you for example have a hearing damage of the outer hair cells, you still have the filters, but they will just be wider because you don't have a sharply tuned cochlea at that stage. So these are the effects of masking, and of course, again, how much does this mean? Well, it means a lot if you have an endangered animal, right? Then still, this is just a fairly mild traffic noise. So if you had a pond where there was the most endangered frog in Africa, and then it could mean something that you had a road going by it, right? Even though this seems to be this is about vulnerability to predation. It's a little bit a dangerous thing, because that's something you will not readily see. Whereas communication ranges and so on are fairly easy to. You can measure the call of the bird, and you can from what you know about its hearing, you can calculate this. But vulnerability to predation is not. That's not so easy, right? And there could be a lot of silent damages that you don't really know about. And so these were the milder effects of noise, and then there are of course the physiological effects, and the most common one in the mammals. 5 minutes, okay. The most common one in the mammals is destruction of the outer hair cells. This is a normal outer hair cell. This is one after a noise exposure. So it's quite dramatic, and eventually these sensory hairs will break completely, and this cell will die, and you will miss the cochlear amplification at that stage. But another one that we are beginning to see here is beginning to concentrate on is the hair cell synapse overstimulation. So imagine that you stimulate at a very high level. You will have a lot of biochemical things happening in your hair cell. You will have a lot of glutamate released, because that's a nerve transmitter for the auditory nerve. And glutamate, interestingly enough, and that's an example of unintelligent design, is toxic in high doses. So that transmitter you release, that actually is toxic to the nerve cells. And that means that even though you have a normal audiogram, you can still have lost some nerve fibers during excitotoxicity. So that's a kind of a hot topic at the moment to investigate that. And then, of course, there's middle ear problems. I mean, you could have direct damages to the middle ear, but that is very extreme. And then you very likely will have had damages to the whole system too. So that will be really bad. And then there's the systemic effects of noise, and I have a few examples here. This is a measure of heart rate in pigs. This is a control. And this is a treatment with noise, and you can see an increase in heart rate of the pig, which you can interpret as a beginning stress response, of course. And here's directly measured the levels of stress hormones, corticosterone and adrenocorticotropic hormone in rats as an effect of noise level, and you can see, of course, a clear increase in the stress level, which have of course, dilatory effects. I just need to run quickly through the temporary threshold shift. This is a measure of auditory fatigue, and the way you do it is that you measure the threshold, auditory threshold, before and after noise exposure. It reflects that you have some repair going on in the auditory system after an intense stimulation. And then the thresholds after some time revert to normal. We did this on slider turtles. We have an ongoing experiment that I would like to show you since we're doing it. So this is a slider turtle in our booth, an audiometric booth. We have electrodes here that measure the brainstem response. And we measure, so we expose them to sound first and measure their normal audiogram. Then we expose them to noise. And after the noise exposure, we measure the audiogram again, and then we measure the recovery. And I have two sets of very preliminary data here, but this is the data on the recovery. So this is just post-exposure, and then the amplitude of the response, the auditory response, increases with time. So you can see in this case, it takes about for this exposure to take about 3 hours. What's that? I'm good. This is another type of experiment. The other experiment we exposed them to for 24 hours. This is just 1 hour exposure at a slightly higher level, and there you see the same. So this is the pre-exposure level before noise exposure. These are the noise exposure levels, And you can see that through hours, from 15 minutes, 30, 45, 165, they sort of revert to normal. So we can measure the temporary threshold shift to this by that double age. And you can do that in a lot of other animals in the same way. And it has been, again, the marine people have, mammal people and the people working on marine organisms are far ahead of us here and have done much more than has been done in the terrestrial system. And the reason why we're doing the turtles is actually to use them as a kind of a model for sea turtles. Okay, so by that we'll end. I think it's lunchtime now.
It's lunchtime.
Okay, cool.